Oh. Okay. Okay, I guess we'll sort of get started for today's session. Welcome to our annual MPAS User Workshop. Following our tradition, and on the first day of our workshop, we have information talks, which hopefully will be of interest to many of our users. And today we are pleased to have two of them. The first one is on Raijin project. I probably didn't even say that correctly, but anyway, it is about developing data analysis tool for unstructured grids. And you'll be given by Orhan Eroglu. I probably didn't say your name right either, but I apologize.
No, that's great. Yeah.
That's
Yeah.
Thank you. He's a project lead from the Computational and Information Systems Laboratory of NCAR. Following the break, we have another talk on MPAS open source development. The talk will be given by Skamarock and Michael Duda of Mesoscale and Microscale Meteorology Laboratory of NCAR. So without any more to say, and please, Orhan, start your presentation. Thank you.
Okay, thank you very much, Wei, for the nice introduction. And I am assuming everyone can hear me well still. So, yeah, I would like to start with thanking to Wei and other organizers to having us here with the very first talk with this first day. It's great. And my name is Orhan Eroglu, as Wei pronounced just perfectly. I have been working at NCAR CISL for almost 3 years now, and I have been leading the GeoCAT group for 2 years. Project Raijin is a recently NSF EarthCube awarded project, and GeoCAT is part of this bigger project, and I have been one of the co-PIs there. For the software development, we are in charge. And you can see my team members in GeoCAT team, as well as Project Raijin. There are many folks from NCAR, as well as we have one Project Raijin member from Pennsylvania State University. And before we get started with the actual presentation, I would like to apologize for my voice if there is any loss of voice. I woke up with some sore throat today, so yeah, I apologize beforehand. Just let me know if anything is unclear due to the voice or anything else. I would like to share a lot of updates about our Project Raijin and Unstructured Grid, as well as MPAS related research and development today. But before we start with that one, I think it is better to start with some GeoCAT background information. So the GeoCAT team, which is in long, the Geoscience Community Analysis Toolkit team, established in 2019. And it leads the software engineering efforts of the National Center for Atmospheric Research, Pivot to Python initiative. GeoCAT team is full of software engineers from diverse backgrounds, from mathematical computation, computer science, atmospheric research, and so on. And the team has 5 full-time software engineers, as well as SciParks interns during this summer. The Python, I would like to talk a little bit more about the Pivot to Python initiative. So NCL was aimed to support the analysis and visualization needs of the global geoscience community for long decades. There was a significant driving motivation, on the other hand, for Pivot to Python initiative, and it was scalability. So yeah, it was to develop scalable scientific software tools for ever-growing data sets in not only unstructured, but also structured grids research. The Pivot to Python roadmap has an initial 2-year roadmap with major milestones that were replicating NCL's computational routines in Python ecosystem, training and support for transitioning NCL people and users into scientific Python ecosystem. And the third one was moving tools into an open development model where community involvement could be prioritized on top of everything for project development. To address this initial roadmap, the GeoCAT team has similar focus on it, and they were creating scalable data analysis and visualization tools on structured and unstructured grids for the geosciences community in the scientific Python ecosystem, and employing an open development model that would help every one of us prioritize community involvement at any level of GeoCAT project lifecycle, alongside having the whole software stack open sourced. On the right hand side, you can see a UML-like general overview of the GeoCAT project structure. There are several software projects under the hood. So GeoCAT has been developing and maintaining several software projects. Some of these have been established so far, and we can consider them as software products. They are still in active development, but it is fair to call them software products because they had several versions released, and they reached good amounts of user bases already. GeoCAT Comp, for example, GeoCAT Examples, and GeoCAT Viz, WRF Python, and NCL are such of these projects that we can call software products. All of these projects, except NCL, is still in active development, while GeoCAT provides only support for significant conda-related issues for NCL. That means NCL is in maintenance mode for a while. But other than NCL, the other software product tools are still in active development. From that perspective, we can call them still a research and development project too. Project Raijin, on the other hand, is more of a research and development project, as it is recently awarded and is in initial stages of development. It is dedicated to unstructured grids research for data analysis and visualization, and I will be talking about Project Raijin in more detail throughout the middle to end of the presentation. And after having the overview of GeoCAT, I would like to share some highlights about individual software tools under the GeoCAT umbrella. The first one is GeoCAT Comp, for instance. It houses computational operators for applications ranging from regrading and interpolation to climatology and meteorology. And you can see the full list of categories that have been already implemented under GeoCAT Comp on the right-hand side of this slide. GeoCAT is built upon the cornerstone Pangeo packages such as Xarray for data input and output, Dusk for parallelization, so scalability, and Jupyter Notebook for mostly documentation and exemplification purposes. Dusk compatibility enables scalability, as I mentioned, from personal laptops to high-performance computing, like HPC systems, such as NCAR's Casper, Cheyenne, and upcoming Derecho clusters. GeoCAT is released through a continuous delivery model in which we release new versions monthly so that we can deliver them as soon as they are implemented. And the same thing applies to our bug fixing approach as well. And on the left-hand side of this slide, you can see some metrics, recent metrics about the user base and everything related to how much it is used so far. GeoCAT examples, on the other hand, provides visualization examples in scientific Python ecosystem, and it provides over 140 publication quality plotting scripts in Python for earth sciences. You can see GeoCAT examples as kind of a substitute and replacement to Pingle, as well as the graphics examples of NCL in the past. So example scripts are implemented by using Matplotlib and Cartopy packages in scientific Python ecosystem, and they are presented with Jupyter notebooks. On the left-hand side, you can still see some insights about how much it is used in the scientific Python ecosystem with the help of some numbers there. And in addition to GeoCAT examples, GeoCAT Viz is another package we have in combination with GeoCAT examples. GeoCAT Viz enables higher level implementation of Matplotlib and Cartopy's low level functionalities. So they can be used through a variety of easy to use helper functions in GeoCAT Viz under the GeoCAT examples umbrella. And on the right-hand side, you can see some recent example plots from GeoCAT Viz and GeoCAT examples combination. They are Taylor and curly vectors. WRF Python, on the other hand, so some of the folks here in this audience can remember from last year, one of our team members, Michaela Sizemore, had presented a WRF Python tutorial in the last year's MQ workshop. WRF Python is working with WRF ARW model outputs and providing diagnostic and interpolation routines, as most of the people here knows. Its active development is kind of limited, but still continued. However, full support is provided for user requests and reports in a daily basis. And Michaela Sizemore is the team member, the essential team member of GeoCAT team who supports the WRF Python user base. And you can see on the left-hand side some numbers and insights about WRF Python 2. So, okay, so far we have mentioned, and whatever we have discussed was mostly about our established developments on structured grids. There was some unstructured grid research and development, but it was really limited. But most of them about GeoCAT.com, GeoCAT examples, and other stuff were mostly dedicated to structured grid analysis and visualization. But the GeoCAT team has also started unstructured grid research. So before I dig into the details of whatever we have been doing so far about unstructured grids, I would like to share some background information as well, and some driving motivations for our team to look at unstructured grid research. So unstructured grid models currently are capable of operating at kilometer scale, or also known as storm resolving resolutions, the resolution at which individual storms are resolved. So it is a stepping stone towards cloud resolving models that would allow simulation of individual large clouds. This is a really strong capability that would come from unstructured grid models. But at the same time, it brings us some problems with the current state of the science. I would like to discuss some of those problems here. So first of all, there is no widely used conventions for the storage of unstructured grid data in the community, including the scientific Python ecosystem. There has been the UGrid conventions, and there seems like a good consensus around it, but from the implementation standpoint, there is still a lot of things to do to have a widely used implementation or tool. The other problem here is there is only a few analysis tools capable of working directly on unstructured grid data. So most of the time, the way to go is resampling the data to lat long, and it has numerous pitfalls of itself. The final thing is a problem here, the global storm resolving resolution, which is kilometer scale, is capable of generating lots and lots of data, which is in turn very much difficulty for not only data analysis, but also visualization. To address all or most of these problems on the unstructured grid research, we have been working on a proposal for a while, which was called Project Raijin, and the GeoCAT team was software development part of that project. And we were recently awarded by NSF EarthCube program for this Project Raijin efforts and proposal for 3 years. So you can see the team for Project Raijin here. And Project Raijin's goal is to enhance the open source analysis and visualization tool landscape by developing community-owned, sustainable, scalable tools that facilitate operating on directly operating on unstructured climate and global weather data in the scientific Python ecosystem. And throughout this 3-year project, GeoCAT will work on the development of data analysis and visualization functions that could operate directly on the native grids, as well as establish an active community of user contribution around it. So open development is still one of the essential goals with this Project Raijin as well. And there has been some driving use cases for the Project Raijin and implementation. So to motivate our work and help define and prioritize an initial set of analysis capabilities, we defined 3 important and representative scientific use cases whose analysis needs we aim to address. So first of all, dynamical core evaluation. When new dive cores are developed, they undergo a series of idealized but rigorous tests to ensure their suitability when used operationally. The second driving use case is atmospheric blocking frequency. It is important, especially for Earth system models, to faithfully capture the statistical characteristics of blocking, because blocking patterns influence the path of storms, impacting precipitation patterns, and they strongly influence temperature and hydroclimate extremes. And the final of these driving use cases is cyclonic storm analysis. For example, tropical cyclones that occur infrequently and are of great importance to society. At this point, I would like to share some insights about what core technologies we are planning to use in the scientific Python ecosystem to realize the implementation of Project Raijin. So to support Project Raijin's open development goal, first of all, its code bases, versioning, continuous integration and development, as well as collaboration activities are all managed on GitHub as GitHub repositories. User APIs are written in scientific Python ecosystem, as we mentioned several times so far. They could be implemented either from scratch or through making use of some widely used libraries such as SciPy or NumPy or others. Similar to the other GeoCAT tools, it is also built on top of the cornerstone pan-geo technologies such as Xarray for data input and output, and Dusk for scalability. So Raijin documentation and examples will be provided using Jupyter notebooks, as we do with the rest of the projects we have. And GeoCAT will be utilized for packaging and distribution as well as testing purposes. And I think it could be beneficial to have a look at the notional component diagram of Project Raijin. So when it comes to the implementation of Project Raijin, we would like to talk about a new Python package, which we call Uxlarray. Uxlarray is actually extending the widely used Xarray package of Pangeo ecosystem. And the Uxlarray will natively support MPAS as well as other unstructured grid models. However, it is also extensible to support anything new in the future if desired. So Uxlarray is designed to provide computation and plotting functions on the native grid, as well as providing some regridding from unstructured to structured or vice versa type of functionalities. And here is a tentative development roadmap, which we originally put into our proposal. It is open to modifications, and furthermore, we have currently been discussing with interested community members on how to prioritize the analysis operators that should be in place for implementation today and for a very long while throughout these 3 years. You can see the tentative plan for other functionalities such as regridding and visualization, as well as some examples provision. And we are foreseeing some milestones that could fit to some GeoCAT releases, where we could release significant versions of Uxlarray for some unstructured grid functionality. To implement Uxlarray, we have partnered with DOE's SEEDS project because both of our groups had very similar essential goals, such as open development, open source, and the content of the proposals were pretty much similar to each other. So we ended up making a partnership to speed up the research and development process. And SEEDS project is adding U-Grid output support to E3SM. Uxlarray is already up and running at the shown GitHub repository here, and there's a QR code for easily reaching to the repository while you are watching this presentation. That first, okay, we will have the first official release in just a few days from now, right after our internal testing is finished. And the first version will have several data input and output functions for varying file formats such as UGrids, Exodus, and script. In addition, we have an ongoing SciParks internship program for the visualization part of the project, where one undergrad intern is working on developing new MPAS and other model visualizations in our GeoCAT examples gallery. At this point, in a good relation to Project Raijin, we have also started to create some new Jupyter notebooks under our GeoCAT examples gallery. Such notebooks showcase different unstructured grid visualization schemes and scenarios. Most of the notebooks are to be interactive with features such as panning and zooming in and out to reveal much greater data fidelity with the unstructured grid plots. The very first example, as you can see the reference here, is an MPAS visualization. The data used in this notebook is courtesy of MQ's FalcoJute. It's an MPAS global storm resolving model weather simulation dataset. It has varying resolutions from 30 kilometers to 3.75 kilometers. In our gallery notebook, which is a pre-rendered Jupyter notebook, we have been using the 30 kilometer one, but today I am planning to give a live demo on the most fine resolution, which is 3.75 kilometers, if everything works with the demonstration well. I have also put a simple video snapshot of that notebook just for the folks' reference whenever they look at the PDF version. But instead of using this video, I would like to bring you to this gallery notebook, which is residing here, and walk you through a detailed demonstration of how the things can be performantly run with 3.75 kilometer resolution when it comes to MPAS visualization. So if you go to the GeoCAT examples documentation webpage or the gallery, you can see a notebook gallery tag here. And when you click on that one, you can see the MPAS example here or here. When you click on this, it first starts with the required information to locally execute this notebook for interested parties. But today, I am not expecting anybody in the audience to run this locally because it requires some configuration. But we could start with some significant information about what this notebook specifically showcases. Then we can give it a try on a live demonstration. So out of these four significant points here, I think it is best to start with the fourth one, the final one. So this is a notebook which compares the well-known matplotlib package in Python ecosystem to data shader, which is a new and less known visualization stack of packages. So unlike matplotlib, data shader stack is designed to perform very well with, especially with large data sets. So when it comes to millions of data, we will see shortly, data shader could pretty much outperform Matplotlib. That's the first thing. The second benefit that would come from data shader stack is the interactivity of the plots. So as you can see here, using data shader stack, which includes data shader, GeoViews, and HoloViews, provides us a lot of interactivity option, and it brings us greater data fidelity when it comes to global data or switching between global and regional analysis. So the plotting is interactive in the sense that you can pan and zoom on the data that is shown, that we will soon see live. And again, it reveals greater data fidelity to research. And one more thing that could come as a benefit from data shader versus Matplotlib is the use of connectivity information that comes from MPAS or some other unstructured grid models. So when we have the connectivity, data shader allows us to make use of it to perform really high performance visualizations. I could say in a local laptop, in a personal laptop, within just a few minutes, you could visualize a 3.75 kilometer data with tens of millions of data points. And one more thing here, when we don't have connectivity information, we would require the costly denoted triangulation that I would shortly show with the Matplotlib. And if you go to this notebook, since this is a pre-rendered Jupyter notebooks, you can see the pre-rendered visualizations here, and they also provide some, to some extent, some interactivity. They are not real-time rendered because they are pre-rendered, but it is still useful for some information. And at this point, I think it is enough to talk about this GeoCAT examples notebook, and we can give it a live demonstration. Let me bring my local Jupyter Lab interface, and this is running on my local laptop. Let me quick see, and we can start with restarting everything to make sure we are reading in the data and generating everything else from scratch. And while we are walking through this notebook, I will be giving detailed information about what implementation part could handle what here. So again, I would like to talk a little bit more about the data itself. So it is the global data sets used in the same experiment, but they have varying resolutions from 30 kilometers to 3.75 kilometers. The data is, as you can see here, of the courtesy of NCAR's Falcojute, and it has been produced through the Diamond initiative, as far as I know. And let's have a look at the MPAS data and variables. So the relative humidity variable is used for the primal mesh of the MPAS model, and the vorticity is used for the dual mesh. And I would like to also say, due to the really large size of the, especially the 3.75 kilometer data, only 2 variables are residing in the data set. After the data introduction, I would like to show cell by cell how to execute this notebook. So this is the first cell which we basically import required Python packages. As I have mentioned before, the hollow views and data shader is for a data shader stack to rasterize and render the data. And other than that, we have been using some back-end engineers, and some visualization related parameters are being defined here too. Other than that, the only thing we know from the scientific Python ecosystem is Cartopy for projections and NumPy for general purpose data manipulation. So it's currently running to import all of the packages required. So we are able to import all of our packages. Then, even though we have a cell for dust penalizations, basically we are not doing any penalization here to just see the actual performance coming from the connectivity information and usage of data shader stack. So you can see all of these are commented out just to avoid the actual penalization that would come from Dusk. So we can just implement this one. We have a number of utility functions here that is generally required for manipulating data. For example, the data unfortunately don't necessarily come in a consistently clockwise order in MPAS model, but the visualization packages such as Matplotlib or data shader stack requires clockwise ordered data points. So we have some utility functions for those type of cleanup and manipulation purposes. So I will just get them interpreted and continue with our actual function. When it comes to this function, I will give you a detailed information because it is important to know how to get the data sets rendered with data shader stack. And this is another one for, I think, primary mesh to triangulate the polygon points. For now, let's start with the loading of the data. And first of everything, I would like to start with, I will be showing this 3.75 kilometer case right after running the simple, shorter and faster 30 kilometer resolution first. Because when it comes to Matplotlib, it is almost impossible to run the Delaunay triangulation with this fine resolution. So I would like to first give you a demonstration of all of the examples being interpreted and executed. After that, we could look into this, how performant this 3.75 kilometer could be also. So let me just read data from 30 kilometer resolution for now. And I commented this out. And again, just for the reference, out of this diamond data, I am only reading in relative humidity and verticity variables, then the connectivity information and getting them rendered through data shader stack. If we have a look at this 30 kilometer resolution data, it has only about 500,000 data points. It is not huge, So we can get both of the examples from data shader and matplotlib denoted triangulation to visualize some plots here. So this very first example is about making use of the primal mesh of the MPAS model and making use of the connectivity information to get the things visualized through the connectivity information rather than needing to perform any Delaunay triangulation. So we are reading in data here, and as you can see, we are reading them as in triangles and making some counterclockwise ordering, as I mentioned before. Then what we are doing here is just creating a cartopy projection, then getting a triangular mesh. So for data shader stack to visualize your triangle points, you need to implement a triangular mesh generation, as we are doing here in the utility function. And it is simply as getting in the vertices and generating an specific object class of triangular mesh or holobius.triangular mesh. So it is just for rendering purposes when it comes to data shader stack. So at this point, we are finished with our triangular mesh generation. When we render the data, we can see the real-time rendered plot. And if I now zoom in, for example, in here, we can see data being re-rendered every time I zoom in or zoom out, in opposite to this pre-rendered and recorded published Jupyter notebooks. In here, even if you zoom in, there is nothing as a re-rendering process here because the data were already read in. But in here, since we are running the notebook in real time, if we zoom in or out like this, like this, data being re-rendered every time when we zoom in or out. And I'm turning back to the global data again. So this very first example is from the primal mesh of MPAS dataset. The second example is to compare how we could visualize if we didn't use the connectivity information coming from MPAS model, or for other models such as CAM-SE, we wouldn't have the connectivity information in first place. So we would need to Delaunay triangulate the data first. It just showcases that. So for that reason, for that purpose, we are first importing triangulation functions from matplotlib, and we are Delaunay triangulating the data points first, as you can see here. Since this is not a really huge data, this is going to be executed successfully with the matplotlib. But when it comes to 3.75 kilometer resolution, that I will shortly show to the audience, it is almost impossible for matplotlib to run successfully within the borders of your local RAM, memory, and CPU borders and limits. So when we run this Delaunay triangulation, it will take some time, but succeed. So okay, it succeeded. When we rasterize and render this, so as you can notice here, we are still making use of the data shader to visualize the data, but under the hood, we are using the matplotlib for back-end hygiene. Again, this is the very same data triangulated through Denoted triangulation and rendered through Matplotlib. And the interactivity functionalities are the same. If you zoom in at any region on the globe, you can see data is being re-rendered and visualized again. And the third example is about the plotting of the dual mesh that come from MPAS dataset. It is similar in implementation to the very first example. And we are done with the triangular mesh creation because the data was not huge, as we mentioned. And rendering is quick. And in this plot, we should be plotting the works there. And the interactivity features are the same. At this point, after we compare Matplotlib denoted triangulation to data shader connectivity information use, I would like to show how it could perform with the actual fine resolution MPAS data, which is 3.75 kilometers. First of all, I would like to get rid of everything we generated as output and restart my kernel just to be comparable to each other. And after we execute all of these required cells, I would like to read data from 3.75 kilometers. And again, this notebook is running only on my personal laptop, which has a limited CPU and memory capability. So in this example, we will be reading in from 3.75 kilometer data. It will take a bit longer than the coarse resolution dataset we used before. It is done, and if you look at one of those variables, we can see there is almost 42 million data points in this data set. So the very first example was, as we can remember, the plotting of MPAS primal mesh with the use of connectivity information. And when I run this triangular mesh creation cell, it will take some time, but it is a very reasonably short time, especially regarding we are using this on my personal laptop. It will probably take half a minute to 1 minute. Rendering could take another 1 minute or so, but in total of about 2 minutes, we would be able to visualize a 3.75 kilometer resolution data with more than 40 million data points, which is great actually. And the interactive plotting functions that comes with it is also additional benefits. We are done with the creation of triangular mesh here, and we now can visualize the data in real time. Since the data is huge, it is probably running up to all of my memory and CPU here, but it is still great that on a personal laptop we are able to do this, and there could be excuse me, what was their question?
No, please go on. I
Okay,
think somebody may unmuted themselves.
Okay.
Go on.
Okay, so right now it is still running on the rendering part of this visualization. It will probably take again another half a minute to 1.5 minutes. So when it is done, we will see here idle and we will see our plot visualized. Then I will show you how this matplotlib implementation could take forever and wouldn't succeed by just running this, but we wouldn't have to wait for it because I'm pretty sure I gave it a try with this fine resolution data. It took forever and couldn't come with any actual results when it comes to below triangulation without using the connectivity information. It is still running. I assume, I think it took 2 minutes so far for this rendering part of it. While it is interpreting the rendering part, I would like to talk a little bit more about how important this thing is in general about unstructured grid research. So when it comes to the data analysis and visualization on unstructured grids, it is vital to make use of. So it is done. It took probably 3-ish minutes about the whole rasterizing and rendering of the 3.75 kilometer resolution data. And as we did before, we are able to zoom in on a region here, and it re-renders every time. As you can see, the change on the plot, it re-renders every time when we zoom in or out. So I would like to give one more. Okay, and again, we can start execution of this cell, but I am 100% sure, as I gave it several tries before, it would never succeed with the Delaunay triangulation of matplotlib because it is too costly of an analysis function to be executed with this high number of data points, like more than 40 million. So I will start this one, but in the meantime, I would like to talk a little bit more about how important this could be in general about not only MPAS visualization, but also in general about unstructured grid visualization and research. So when it comes to visualization or data analysis of unstructured grids, it is vital to make use of the connectivity information. So in Uxlarray, or in general, in our project Raijin, we are focused on making use of the connectivity information so that we could be able to run whenever possible the functionalities directly on the native grid. So this is our focus, and it is not always easy to make performant the high use of connectivity information, but the team is focused on that end, and it would probably bring a lot of opportunities to MPAS as well as other model visualizations in the foreseeable future. I think at this point, so it is still running, and again, as I mentioned, it will run forever without bringing any actual outputs on this data. So it shows also how vital the connectivity information usage is important, and how performant we could go with the making use of it. So it is impossible from this end with the de Novo triangulation if we didn't use connectivity information. So that probably wraps up my not only my demonstration but also my presentation. I am turning back to it just to see what else we have here. Okay, yeah, so it was the latest slides. So I put some contact information as well as some links here for the MQ community to get involved if they ever get interested in any of these research and development stuff. Again, we are an open development group, and all of our projects are handled in an open development fashion, which means we are 100% both welcoming and needing the community input and feedback. So please do so if you are interested. And at this point, I'm stopping my presentation and would like to hear if there is any questions.
Okay, thanks, Orhan. There are two ways you can ask questions. You can raise your hand, and so that we'll call you to speak up, or you can use chat to type in your question. Erhan, there is a question actually coming from YouTube streaming, and someone is asking, will Uxlarray support NICAM, NICAM, NICAM model? You've heard of that model?
ICAM or ICOM? Icon, did you say, Ray? Or
NICAM, NICAM.
NICAM. I'm not sure if I heard about that model, but we are planning to support CAM-SE models as well as ICON models. And one more thing here is, even if we can't support originally some of those models, because there are scattered number of models in the community as well for when it comes to unstructured grids. Even if we cannot support them initially, our Uxlarray is being designed in a way that someone else could come and propose their model to be supported. They could contribute to our library, the support, and we could provide them with the actual interface to how to put that contribution, or we could just discuss and see how we could further proceed.
Okay, so I hope someone listening on YouTube will hear this. A couple questions from the chat.
Yeah.
Can you read them? Can you see them?
I can read them. The first question is about what did you visualize again from Garden, and was it 200 megabyte vorticity? The final part, the example number 3, let me see if I can pull that back. Example number 3 should be the vorticity, and example number 1 is relative humidity which is a data set interpolated to 200 HP. So let me pull this one instead. So yeah, this one, the example 3 should be the vorticity, while example 1 should be the relative humidity at 200 HP. Is that answering your question, Gordon? If not, please let me know, raising your hand or putting into the chat. The second question here is from Kelly. Can this notebook tools be used for regional MPAS outputs? That's a great question, and you are not alone, Kelly. We have received similar questions from different people so far. Yes, we have been currently doing some research through our SciParks internship program about that, as well as you can also please feel free to provide any details through our GitHub discussion or issues, but we are expecting to come up with some solutions there soon on regional analysis as well. And the third question is from Koichi. Thanks, this visualization example in Jupyter is great. Just curious if it would be also possible to develop a simple viewing visualization program, just like NCView for unstructured grid. Honestly, I don't have any experience with NCView, but what I can understand from your question is you are asking for a simple graphical user interface that you could just read in with the help of a number of buttons, for example, or maybe through terminal. You could put in some files and then get them plotted. Is that correct, Koichi? If
yes, exactly. Just on the terminal, and then just one command, and pop up in the map view.
I see. In the Python ecosystem, having graphical user interfaces and turning these type of functionalities into some graphical user interface or desktop application kind of tools is not always the common way to go. So Jupyter notebooks are commonly believed and used as the general purpose, quick, practical ways of visualization. So that said, I am not sure if we could go that way, but yeah, I'm not sure for today if it could be the way for us to go as the GeoCAT team, because most of the feedback, if not all, most of the feedback is about people use Jupyter notebooks with their analysis and visualization purposes, and they are just fine. But I would still like to see how, or if there could be anything that we could and the community could benefit from an NCView like approach here. Thank you very much for the feedback. And if Alisa and Michaela from the GeoCAT team is in the call, could you folks please at least make a note of these questions so that we can revisit them afterwards?
Thanks so much.
Okay, yeah, sure. Gordon says thank you, so I think I can assume my response was kind of answering his question. The next question is from Emmanuel. Does the program at first regret the data and then visualize? No, it is directly being handled on the native grid, and it is the strength we are talking about. So most of the current scientific workflows, even if they are individual on like people's own desks, they are still very much relying on regulating the data first. But in this example, there is no regulating to lat-long grid. So we get the data, we get the connectivity, and then we get them rendered directly from the native grids. When it comes to data without connectivity information, I don't know for today how performant we could do that, but yeah, it is the current strength with the data, MPAS data, for example, with connectivity information. Kelly Nunez also said, thanks, thank you very much for all of your questions as well. A related question from Koichi is, we need connectivity information because data shader or GeoViews hollow views requires the information to render the fields. It's a question. So, Koichi, if we don't have a connectivity information in the unstructured grids, theoretically, we can still visualize them with the help of Delaunay triangulation. But the problem with the Delaunay triangulation is, especially with huge data sets, when it comes to tens of millions of data points, as we have seen today with the 3.75 kilometer resolution, Delaunay triangulation with the current matplotlib implementation or wherever it is implemented is almost impossible to come up with the actual outputs of triangles that could be generated from your data points. So when it comes to larger data sets in unstructured grids, yes, having the connectivity information is a great benefit, and having that is not enough. For example, if I didn't use data shader visualization and rendering today, I would still be needing to use matplotlib Delaunay triangulation, because to my best knowledge, there is no way to make use of connectivity information in the matplotlib visualization stack today. I am frequently referring to matplotlib because it is the best known visualization package in matplotlib Python ecosystem, but it is away from being sufficient for unstructured grid visualization needs for the future, especially with larger data sets. I hope it was clear, but yeah, when it comes to unstructured grids with tens of millions of data points, if there is the connectivity information, we should 100% use it for high performance visualization capability. If there is no connectivity information, I don't know how, but we should find scalable ways of triangulating the data first. And it doesn't seem like the matplotlib Delaunay triangulation could be sufficient for large data applications as of today. There was the second part of, Koichi says, in other words, we need connectivity information even when we plot variables defined in the cell centers instead of the vertices. It's a great question, and I would like to think about this a little bit more, and because yeah, if we had the points on the cell centers, I would still assume we would need to triangulate them, but I would need to study and think about a little bit on that question. Emmanuel says thank you, and there is a question from Rob, or maybe a contribution. Verdi is a visualization tool that is compatible with MPAS. I don't have any information about Verdi, but maybe my quick question is Verdi a Python tool or easy to use Java program? Yeah, not only Verdi or not only Java language, there might be different tools around the unstructured grid research, but our point is they are pretty much scattered. I'm not talking about anything like strengths or weakness about these tools. I'm just saying those are scattered. It is not the easiest way to know about all of them or make use of all of them on our individual workflows. It is one of the strongest motivations with NCAR's Pivot to Python initiative. So the scientific Python ecosystem is huge with a lot of problem-oriented packages that have been implemented and well used so far. So our point is about making kind of a potential to be commonly used in the Python ecosystem, because for example, since Verdi is mentioned, let me just talk about that. It is implemented in Java language, and if we want a new feature, I don't know how easy it could be to get that feature in Verdi in a reasonable time. But in Python ecosystem, with an open development approach, we can assume if someone else, just like the question that came from Wei through the YouTube streaming, if someone else would like a support about a specific model, the implementation is there with its sources open and with the support from the team to receive contribution from the community. So it could be really easy to contribute support for more models or more functionalities into a package in Python ecosystem. So that's my my thought, but it doesn't mean Verdi, you know, shouldn't be useful or shouldn't be looked at. So if either Anissa or Michaela can make note of Verdi tool and its link, we can also have a look at that, at least to see what features they are providing already. Koichi made another point here, which says, I think I understand the answer about connectivity triangulation. Thanks for the explanation. Thanks, Koichi, and please feel free to reach out to us through maybe email or GitHub discussion or wherever works for you. And for that purpose, not only to Koichi, for whole audience here, I would like to share, as I am still sharing my screen, I would like to share a good explanatory diagram to how to reach out to us with the most convenient way you would like. I would like to show contact information from Raijin websites. So this is our Raijin project website, and if you check contact us page, we have put a self-explanatory diagram to help people to determine which way to reach out to us. I don't know why it didn't appear here, but there's a diagram here. Okay, so it is kind of to guide the people to see if whatever the problem or discussion point they have, which way they could easily reach out to us. But again, from email to GitHub discussions to Zoom messages to anything else as a communication channel. We are more than happy to receive feedback from the community. So please feel free to reach out us and let us know your thoughts or feedback. Thank you, Coach. And I would like to ask Wei if there is any other question that is coming from YouTube streaming or anywhere else.
No, I don't think we've seen more from the YouTube side, but thank you very much for the for the presentation, and thanks to everyone for the lively discussion. And we will finish this session, this part of the morning, and come back for the next talk in about 20 minutes.
Thank you, everyone, for joining me, and Wei, thank you very much for you again for having me here. It was great, and we are very much open to MQ talks, feedbacks, and any involvement.
Yeah, thank you. Yeah, I think we are aware that that's, thank you.
Yeah, sure.
We'll see you in about 20 minutes, everyone. Michael, if you're ready and would like to bring up your slide.
Yeah, I can do that.
Okay, okay. Looks good.
Okay, sorry. The unmute button moves from the bottom of the screen to the top of the screen. So that takes a bit of finding.
Just wondering, do you need us to monitor the chat question for you guys?
I don't think so, Wei. I think we're probably good with that.
You can, okay, work together. Okay, all right. We'll be here. We'll be here. Yeah. Yeah, if you're ready, Bill and Michael. Yeah.
Okay, thank you, Wei.
Yeah, start.
Well, greetings, everyone. For the next hour and 25 minutes, Michael, Duda, and I are going to discuss open source development for MPAS Atmosphere and how you can contribute to this development. Our intent is to open this process up as much as possible because we realize that community contributions are critical to evolving the modeling system forward, as we've seen, for example, in WRF. And in particular, we really want to expand the development opportunities, as you'll see in the presentation. And we want to expand it beyond what typically has been the case in WRF and MPAS development up till now. Next slide, please. So I'm just going to briefly introduce things here, and then Michael's going to take over. So we're going to talk about the development process that's currently in place and where it's going, some things about how the model is structured that it will help those considering to contributions in those areas. We'll have a short break. Then we'll come back and talk about areas where contributions, we really feel we need them, and the very briefest of summaries that'll lead us into questions and discussion. Next slide, please. So MPAS Atmosphere, it's open source, it's out there in GitHub. It's only the atmosphere and land, even though there are other dynamical cores, for example, ocean, sea ice, land ice. It's not itself an Earth system model. We both have global and regional capabilities, so it has some similarities to capabilities in WRF, but it doesn't have nesting like WRF does. It's different. We do have annual tutorials, and we do provide releases like WRF, only not on a schedule as WRF uses. Importantly, we also have a GPU-enabled branch that we've released, and we'll talk a little bit about that. And we have data assimilation components for it, both DART and JEDI. We started developing MPAS because we realized we needed a modeling system that behaved better on the globe for global simulations than did WRF on its lat-long mesh. We also wanted a clean sheet of paper with software engineering, et cetera, so that we could use more, well, different techniques than are used in WRF, because we realized we had to adopt ultimately to accelerators and a lot of other things when we started out on this path. And that's what we're doing, and it's allowing us to explore how we enable GPU capabilities. But perhaps most importantly, the one I'd like to point out is that this also, MPAS atmosphere allows us a pathway to Earth system model capabilities, which I think are critical to weather research in addition to climate and subseasonal, seasonal prediction, et cetera. So we'll talk about that in a moment. Next slide, please. So essentially, MPAS is open source. It's available on GitHub, and our development branches, where we're actively developing, are also available on GitHub and open source. So they're all out there and you can see them. We have a license so people can use and modify it, but they can't copyright it, and et cetera. But it has an open source license. You may also have your branches on GitHub, in which case they're likely open source too. So I think everybody appreciates that this is the way the world is going, and I think there's a lot to be said for that, because it really allows for this open development process. And that's what we want to try to move more and more to. So we want to transition to open development in addition to the open source that we already have. And in this case, we want to enlist the community in this open development. There's already some members of the community that are taking advantage of that, but it's a very, very small number. We anticipate, and we will remain as gatekeepers for this development for MPAS atmosphere, we being the development team at NCAR, because there's a lot of work that goes into that, and a lot of capabilities one needs to provide and oversight that needs to happen for it to run smoothly. That's some of what we're going to talk about today. Importantly, what's the process to contribute to open development is important, because it keeps us sane. It allows us to do things in hopefully an efficient manner, and that's a lot of what we're going to talk about today. Next slide, please. So traditionally, contributions go to physics and dynamics, particularly physics. For example, if you think about WRF, most of our physics came from the community through a not quite open development process, but in a way it was. But we also take in a lot of pre and post-processing capabilities for MPAS through this. And we've seen in the case of WRF, and somewhat in the case of MPAS, some system configurations that came in. The areas we would like to encourage more participation in an open source development mode is, for example, for users guides, tutorial materials, web pages, and forum participation. And that's where we're really looking to strengthen the community contributions and help us move this system forward as a community. So in our intent, in terms of those other aspects of open source development that we talked about, is to have all this material in these open repositories, in particular the user's guide, tutorial materials, web pages, et cetera, so that people can access them and contribute to them. So that's part of what's new that's coming along. Next slide, please. So the other aspect of MPAS atmosphere is that the dynamical core and some of the physics will be used in an Earth system model, in particular NCAR's Earth system model, CISL, the community for the Earth system model that NCAR supports. And we're bringing the MPAS dynamical core into CISL as part of a project called SEMA, System for Integrated Modeling of the Atmosphere. Next slide, please. And essentially, this is bringing it into the community Earth system model in NCAR, and MPAS is brought in as a dynamical core into SEMA. There's other dynamical cores in SEMA. There's the spectral element core SE, which you heard mentioned a couple times in the last talk this morning, and also FV3. And essentially, by bringing MPAS into SEMA and CISL, we have access to coupling to an ocean model, other land models, sea ice and land ice, et cetera, that are not available right now with an MPAS, at least a couple of modes. So this is another place where if your applications are using MPAS in an Earth system modeling framework, you can also make contributions. Although CESM has its own structure for doing that, it is an open structure, and there is some aspects of open development to it. Next slide, please. I mentioned GPU capabilities. Our current release is, a lot of that came about because of interactions with a number of outside partners, both IBM and the weather companies, NVIDIA, a few group up in Wyoming, University of Wyoming, that helped with a lot of GPU ports of our capabilities. We have that development that's in a release branch out there right now, but it's separate from our main release. We're looking to evolve that forward. And this is really exploratory work in the sense that the community, I don't think, really knows the best way to take advantage of accelerators on current architectures, and we're learning as we go. So there's lots of scope for contributions here if you have the desire and the skill set, I would say, to explore those possibilities. Next slide, please. So you can think about applications of where you can contribute from how you might interact with MPAS atmosphere. For example, you can be just a user where you're contributing bug reports, participating in a forum, or maybe just saying, well, we'd like to see these kinds of things and giving us feedback into where our development directions go. You can be a more active contributor, which would contribute bug fixes and other things, or you can be a developer where you're really developing a major component to MPAS. Some of us sit in all three of these categories. So this isn't a hierarchy we're trying to say is absolute or anything like that, but it gives you an idea of where things sit, and we're looking for people who may sit in any of these categories to help contribute to MPAS as we move it forward in this open development paradigm we're developing. Next slide, please. So towards that end, that was the introduction, and now I'm going to hand it off to Michael to talk about the development process and other aspects. Michael.
All right, so jumping right in, we're going to talk a little bit about the current development process that we use for MPAS, but also project forward a little bit and talk about some of the things that are maybe a little bit more aspirational that we'd like to do in future as we bring in a bigger community of contributors. So the first thing that I'll say is that in general, our development process relies very heavily on Git and GitHub. So these are the tools that we use almost exclusively for our development in repositories. And so I think there's an expectation that anyone who wants to get involved in making code contributions to MPAS would have some skill in using these as well. So I'd say the first thing is that anytime that you invest in becoming proficient in GitHub, but especially Git as a command line tool, in my completely unbiased opinion as a software engineer, would be time very well spent. And you might have heard that Git can have a bit of a learning curve. And I think that's true, but if it's explained in a good way, then it's not too bad to pick up. So to that end, I could recommend the Pro Git book. So it's freely available to read online in, I don't know, over a dozen languages. You can also buy a copy of the book if you want, but if you go to git-scm.com, you'll find links to that. So that's an excellent resource if you want to get involved, but don't yet have a lot of proficiency in Git. So I'll also point out that at present, we unfortunately don't have a lot of written documentation for the process that I'm going to describe over the next handful of slides. Our development group so far has been fairly small, and that means that it's easy for us to communicate these things by word of mouth. But we absolutely recognize that as we open up development to a broader community, we need to have some sort of written documentation because, me walking down the hallway and talking with you is not a scalable approach. So we do intend to have a contributor's guide, and you can take the things that we're going to talk about here as a very fundamental basis for that. And the idea is to expand greatly on these things and get them into a written form in the next few months. So, maybe by end of summer, if you're in the Northern Hemisphere, I guess. So At a very high level, our current development process for not just the model repository, but in general, any repository looks something like the following. And we'll go over these points briefly, and then we'll expand upon them in some later slides. But the first step is almost always to initiate a discussion with others. So open up a dialogue with users, other contributors, and maintainers, and just discuss what it is that you plan to do and get some feedback. And so after you've reached some sort of consensus that, all right, yeah, this is what we want to do and this is how we want to do it, the next step is, of course, to develop those changes. And here we do all of our development in branches of the repository. And furthermore, we do that inside of what are called forks of the repository. So a fork of a repository is a GitHub concept. And the idea is that a fork of the repository is basically your own copy where you can make commits, delete commits, make new branches, do whatever you want. And that doesn't in any way negatively impact the main repository. So it's kind of your own sandbox. You can feel free to explore, develop, and make mistakes. So after we've finished our development, the next thing is to open up a GitHub pull request. And that essentially is the means of proposing that changes in a branch be included in usually the main development branch of the main repository for the project in question. And then that's the thing that initiates the review process. So this is a chance for other people to make comments and say, all right, I tested it with this compiler and found something that didn't work, or this line of code looks suspect to me. You said less than, should that be less than or equal to, that sort of thing. And then after all the testing is finished, that's when we merge that pull request into the proper branch of the main repository. And that effectively wraps up that development cycle. And then we repeat and repeat until we get enough new features to make a release. So we've talked about these things, almost implicitly assuming that we're talking about development of Fortran code in the main MPAS repository. But it is worth pointing out that the same process is probably applicable to just about any sort of development that we can envision doing for any repository. So whether that's contributing changes to a web page or to adding new content to the user's guide or things like that, you can look at this process and say, all right, something like that probably would apply equally. So I said that the first step is usually to initiate a discussion. And there are cases where this doesn't apply. If you just want to fix a typo in the code, you don't need to get feedback from other people to say, is foo spelled with 2 O's or 3? You consult a dictionary and you find out that foo is spelled with 2 O's and you fix the typo. But for any sort of significant contributions, the idea is that you want to probably get feedback from not only the maintainers of the project, but also other developers and even other users who might not themselves be doing any sort of code development. So from the user community, we found that it's possible to get some really excellent feedback in terms of improving the usability of whatever it is you're planning to develop. Sometimes you get feedback from people who say, well, that's really great, but if you were to modify that to make it just a little bit more general, it would apply to my use case as well. So in general, getting feedback from users is a really great thing. And we do that by starting up this discussion before we even start doing any sort of development. Getting input from other developers is important primarily for 2 reasons, and they're closely related. But the first idea is that you might be able to identify collaborators. So you've got some idea for a way to improve, let's say, the MPAS framework. And it turns out there's someone else at another institution who had the same idea. And by starting a discussion in a public space, you can draw out these people who had similar ideas and maybe perhaps collaborate with them. But the more important point is that we don't want to have any sort of duplication of work, because if we've got 2 people who are independently working to implement the same physics scheme in MPAS and they're not talking to each other, one of them gets their changes merged in first, there can be hurt feelings, from the person who said, well, you got your version merged in only because you had more time on your hands to make a pull request before I did. So, we don't want to duplicate effort. We're all rather strapped for time and other resources as it is. And then lastly, it's important to get some feedback from the maintainers of the project. So in the case of MPAS, that would be MPAS maintainers at NCAR, I suppose. And the idea here is that you can get some pointers on, maybe there's a more standard way of doing things, something that's more in line with the MPAS philosophy when it comes to code, or maybe the maintainers can point out, by the way, did you know that we already have infrastructure that does this? There's no need to reinvent the wheel here, or that sort of thing. And then lastly, and probably the most important thing of all, is to make sure that the thing that you're going to be spending a lot of effort on is something that would even be desirable in the main repository. And I want to make clear that that's not to say that we think that anything is not valuable or really excellent work. But if you're working on something that modifies basically every file in the entire repository and yet would only be usable by a fraction of a percent of users, however great that is scientifically, maybe it's just not a great candidate for inclusion in the main MPAS repository. So that sort of thing. So as with many things in life, basically communication is key. So where do we start these discussions? Right now, some of you may have noticed that if you go to the WRF MPAS forum and you go down to the MPAS atmosphere support section, you'll see that we do have a sub-forum called code development. So that might be the place that if literally this afternoon you wanted to start talking about some ideas that you had, or even ask questions about the development process, this would be a place you could go. However, a very interesting alternative is to maybe enable GitHub discussions for all of our repositories. And this is something that we haven't used so far. And I'll admit that I'm only vaguely aware that they exist. But looking around, it seems that these GitHub discussions are almost exactly what we're looking for. But again, they're not enabled in the repositories right now. We just haven't ever used them. So we'd especially be interested from anyone who might have used these in any other sort of development project on GitHub. Did they work out well, or do they have some strange quirks that made them less than useful or less useful than they might otherwise have been? So I would say maybe barring no negative feedback, this is probably something that we'll try to enable on a per repository basis. And maybe this might ultimately be a better place to start discussing development. So just a few side points about hosting questions on GitHub. So whether we ultimately decide to have development discussions on the forum or with GitHub discussions, the key point is that GitHub issues with a capital I are probably not the place for general discussions or to ask for help. So the breakdown looks something like the following. If we want to discuss development, I would say either go to the code development section of the forum, or probably more likely, start a discussion on the repository where you'd like to make the source code changes. GitHub issues, on the other hand, are what we use to track. They're kind of like our to-do list, tracking action items sort of things, or bugs that we know need to be fixed. But in general, if you're just looking to ask questions, I'm trying to run the model and it's crashing, that sort of thing, definitely do not use GitHub issues for those. Please post those to the forum. So to quote GitHub, they summarized it much better than I could in 3 bullet points. Discussions are great for questions and ideas that require team communication to make a decision, while issues are defined pieces of work. So I think that's the key idea here, is that we don't want people, asking general support questions in our development discussion areas. So I realized that not everyone here may be all that familiar with Git, and we're going to be talking about development process with Git for a few more minutes. So I thought I'd give, it's probably a bit more than 60 seconds, but a short intro to. Hey, your microphone. Thank you. All right, so on the left here, we've got a cartoon of a very simple Git repository. So we've got a couple of branches called release and develop, and we've got some commits there. And so there's there's many things in Git, but there's just a couple of things that I want to point out for the purposes of our discussion here. So the first idea is that in a Git repository, we have commits. So these effectively capture the complete state of the repository at some point in time. And not only do they capture the differences from their so-called parent commit. So in some sense, there's a delta, although they're not quite stored that way in Git. But in addition to the state of the repository, there's a commit message. So this is the way that we can describe the purpose and the methodology, for example, that was used in getting the repository into that state relative to its parent or parents. And the key point here is that all of these commits are identified by a unique hash. So this is a SHA-1 hash. I think they're normally about 160 bits, so 40 hexadecimal characters. But the key point is that we can usually get by referring to commits in a repository with about the first 6 or 7 characters of their hashes. So all of these blue boxes here represent different commits in this toy repository of ours. And these arrows represent parent pointers. So we're saying that commit C981C7 inherits from or derives from commit 4AB1E3, for example. So we've got commits that all have parents in the repository. And the second thing that we'll talk about is branches. So the idea is that a branch is just a pointer or a reference to a particular commit. But the key point here is that you can extend a branch by adding more commits to it. So with just 2 concepts, commits and branches, there are a few things that we can talk about doing in a Git repository. So the first thing is starting a new branch. And the idea is that you can add this branch pointer starting at any commit you want in a repository. And in this case, we're saying that we want to start a new hotfix branch that starts out looking the same as the current release branch, but the idea is that we'll add some commits to this hotfix branch. And so that's the second thing we can do. We can add new commits to the top or the head of a branch. So you'll notice that we've added a commit here, C384AC, to the hotfix branch. And we've committed that specifically to the hotfix branch and not to the release branch. So although hotfix and release started out referencing the same commit, we've committed specifically to one branch and not the other. And then once we do development on one of these branches, we'd like to integrate or merge those changes back into some other branch. For example, the release branch in the case of a hotfix or bug fix branch, or into the develop branch in the case of some new feature that we're developing. And we do that with a merge. So the idea is that a merge is just a commit, but critically it has 2 parents. So this merge commit here, 47AAC3, that integrates the changes from the hotfix branch, inherits not only from the hotfix branch, but also from the previous head of the release branch. So through these merges, we can integrate changes from one branch into another. And those are, I think, the key ideas to understand when it comes to Git repositories. So in general, you'll be doing development on branches in your own fork of a repository on GitHub, as we said earlier. And in the interest of time, I won't go into too many details here, although I'll be happy to talk about it during the question session after this. But essentially, it is worth giving some thought to where you want to start your branch when you do new development. So to keep things short, essentially, if you're developing a bug fix, you're trying to fix a bug, in an ideal world, I would say it's best to try to start that bug fix branch on the commit where that bug was first introduced. Secondly, if you're developing a new feature that doesn't require cutting edge work in the main development branch, there are some advantages to starting that development work off of the latest release. For one, it means that any collaborators who might be working with the latest release code can then say, all right, I'm going to merge your new, let's say, adaptive time step work into my MPAS 7.3 release code and ensure that I only pick up just those adaptive time step changes and not a whole lot of other things that are going on in the develop branch that maybe haven't been as thoroughly tested. And then lastly, by process of elimination, if neither of the first 2 apply, then just start your new development branch somewhere on the main development branch to get all of the latest capabilities that you need in order to accomplish your work. So as we commit changes to this new branch, as we said earlier, every commit has a commit message. This does have an author and date. So this is something that you may need to set up the first time you start making Git commits to make sure that the author name is something sensible and maybe use a reasonable email address here. And then the commit messages, as we add commits, do have a particular form. I mean, in principle, you can use any form you want for a commit message, but we are trying to be a little bit better in MPAS about using commit messages that have a single summary line that's usually 80 characters or less. And without going into details, there are many good reasons for doing this. And then a blank line, and then as many sentences or paragraphs as you need to fully describe not only what it is you're doing in that commit, but also giving people some idea of how you're doing this change or why you've decided to do things in a particular way. And maybe, for example, if you're doing some work based on a paper, why not give a reference to that paper in your commit message as well, for example. And so we can continue to make commits on our adaptive time step branch in this example. And the last thing that I'll say about developing your changes is that it really is advantageous if you can ensure that every commit that you make leaves the code in a state where it can compile and run, even if it doesn't fully, make use of the thing that you're developing at any point. So this is helpful when testing. It means that we can break apart a really complicated development into individual pieces that each are guaranteed to do something useful and leave the code in a working state. But when we're tracking down bugs, this is particularly useful. It allows us to employ a process of bisection to find the commit where a bug first appeared. So the idea is that we're doing some work and we say, oh, it looks like there's a bug in our work here in commit 714 DCD. If we can go backwards and look along the chain of parents, so find an ancestor to get a little bit anthropomorphic here, find some ancestor commit where the bug doesn't appear. Now that tells us that, the bug somewhere was introduced between, 9D5C90 and 714 DCD. So what we can do then is to pick a commit that's halfway in between those and test that. And we can do that because, as we've said, every commit leaves the code in a state where it can compile and run. So let's say we test commit B02D39 and we find that it works. So right now we know that the bug was introduced some point after that, and we've already cut our search space in half. And so we can do that again and again to ultimately figure out that it was commit B61ABB where the bug was introduced. And again, if we've used useful commit messages here, then hopefully looking at the changes in that commit and reading the commit message, we'll be able to pretty quickly figure out, oh, I see, someone thought that they were taking, putting an upper bound on a coefficient, but they used the max function instead of the min function. So it was a logic error. Okay, we probably should have caught that during testing, but better late than never. So that's the idea, is just try to ensure that every commit leaves the code in a working state. So just a couple of final thoughts about commits. As you probably gathered from the previous slide, it is helpful to try to break up complicated long development into a series of smaller commits. And this is my opinion, but I think I share that with a lot of other people, that it is a lot easier to review and to debug large changes that come in bite size or digestible pieces. You can break each one down and say, all right, at this state, are we doing something reasonable? And am I convinced that we have done this thing? We've propagated new build options down through all of the make files, and that's the only thing we're doing in this commit, sort of thing. So it's helpful when reviewing pull requests, as we'll see, I guess, a little bit. But secondly, I'd really like to encourage everyone to take some time to write good commit messages. So if you spent several days doing some code development, why not take, just 5 minutes to write, a nice paragraph that really accurately and concisely describes what you're doing and how you're doing it. So the idea is that, certainly what you were doing in a commit, but there's, hundreds, thousands of other people who might be looking through the repository either now or years from now, and they might want to really understand, again, not only the what, but the why of a particular commit. And this feeds into the second point, that as a community model, as an open source model, there's surprisingly a lot of people who look through the repository. I've gotten emails from people who said, yeah, so I was looking through the commits and I saw that this commit said this. And I was shocked the first time I saw this. I said, wow, people actually read the commit messages. And so because MPAS may be used for teaching purposes or other reasons, people looking through the commits because they want to, get spun up on the current state of development, it really does make life easier for other people if you use really descriptive commit messages. And then lastly, the idea is that any sort of effort that we invest in trying to make our work as understandable as possible to other people, that helps us to draw in contributions from a much broader community, and that's to our benefit. So we can get computational scientists or computer scientists interested in our code. They might not care about atmospheric simulation, but they care about optimizing and parallelizing code. And certainly, it's to the benefit of scientists, but also HPC industry contributors who might say, we're running profiling tools on your code and we found something interesting here. And looking at the commit message, it seems that someone was trying to do this, but we think that there's a better way of doing that sort of thing. So long story short, it really is, I think, to our collective and mutual benefit to make good commit messages. I could probably talk for half an hour about this, but I'll stop right there. So after you've done your development, let's say on our adaptive time step branch, the idea is that you're ready, you're happy with the state of your branch, and you want to get those changes integrated back into the main repository. So let's just say that you're some developer named MG Duda, and you've developed all of these adaptive time step changes in your fork of the repository on GitHub. Now we want to integrate those, and we need to determine firstly which branch in the main repository we'd like to integrate those changes into. So it turns out that, based on our workflow, we don't generally integrate feature branches directly under the release branch. So we typically like to integrate things into the main development branch where they can be further tested before we split off a release branch for the next major release. So the idea is that when you make a pull request on GitHub, effectively you're proposing that we merge the head of your branch onto some target or base branch in the main repository. So conceptually, we're requesting that there be a merge commit whose hash is yet to be determined, merging the head of our adaptive time step branch onto the head of the development branch, again, in the main repository. So when you do this, when you open up a pull request on GitHub, you get a screen that looks something like this. So, of course, in this case, we're proposing to merge the adaptive time step branch from our fork of the repository onto some base branch. So it's here that we'll choose the correct base branch. It turns out if you get it wrong, it doesn't matter. You can always edit the pull request to choose a different base branch. But that's the idea. It's at the stage of making a pull request that you determine which branch you'd like to merge your changes onto. But then more importantly, probably most importantly, and I really mean that, is to write a very nice and thorough description of not only what your pull request is doing, but how and why it does it. And as you can imagine, this is really helpful for reviewers who have to look at these code changes and assess whether they are in fact solid and ready for inclusion in the main repository. So just a couple of notes about these pull request descriptions. So when we merge a pull request, unlike in WRF, we usually do this on the command line, just using the git merge command. And so we typically just take the pull request description that I just highlighted on the previous slide, and we use that almost verbatim as the merge commit message. So I just spent a couple of minutes, talking about how important commit messages are. And given that we're using the PR description as a commit message, that implies that you really should write a nice pull request description. But because we're using this as a git commit message, any sort of figures that you include in the PR description don't end up in the commit message, which is text only. So I would say, really try to describe your pull requests well using just words. Although it is certainly, encouraged to use any sort of figures in the follow-on discussion of your pull request, but in the description, try to describe it, accurately just with text. And also try to make the pull request descriptions as self-contained as possible. This just makes it easier when people are browsing through the commit log. If you see something that says, fix bug in issue 418, you say, well, what is issue 418? I have no idea. So now I've got to go open up a web browser and I've got to go to GitHub. And it turns out I'm on an airplane over the middle of an ocean and I don't have internet access. So I'm going to have to just speculate as to what issue 418 was. And furthermore, this doesn't even tell me, how you decided to fix issue 418. I have to try to guess just looking at the code diffs. So that's to say, again, use nice descriptions of your pull requests. And we haven't enforced the use of any sort of template in pull request descriptions, but for example, WRF does this. And this is something that perhaps we could consider doing in MPAS as well if people would find that helpful. So after you open up a pull request, that initiates the review process. So we as maintainers will assign one or more reviewers to the PR. And it's certainly possible for reviewers to leave general comments. But what we tend to do quite often is to ask questions or leave comments referencing specific lines in your code changes. And this opens up sub-threads of discussion where we can say, all right, in this line, I have a specific question about this, or, is this really correct? Or here's a different way you could have done it. What do you think about that sort of thing? And in general, what you'll do as a contributor to address these reviewer comments is to push additional commits to your PR branch. In this case, our adaptive time step branch, for example. Well, not in this example on the screen, but the example that we were talking about earlier. And then at the end of all of this, you've ended up pushing a whole bunch of little cleanup commits what you'll probably want to do, and what we don't really have time to talk about now, is to rebase your branch to clean up the commit history, so we don't have, a dozen small commits that say fixed typo pointed out by reviewer, oops, fixed compilation error with GNU compilers, and that sort of thing. So this is also the stage at which we want to test pull requests, and I have to admit that we're not doing all that great when it comes to automated regression testing right now. We essentially don't have an automated regression testing suite, but we're working on it. And so for now, as maintainers, our commitment is basically to ensure, through right now manual regression testing, that any new contributions don't break existing code. In other words, that there are no regressions introduced by a pull request. And it turns out that we have access to a fairly broad suite of Fortran and C compilers. And probably many of you have found this, that different compilers are good about pointing out different code issues or turning up errors that other compilers just let through. So to the best of our ability, we'll also test with the full spectrum of compilers that we have access to and give you feedback based on that. But as a developer, we expect that any new code that you contribute has been tested and ensured to work with the two modes of parallelism that we support in MPAS. That would be MPI parallelism and OpenMP parallelism. And we'll also expect that you will have tested this new code, this new functionality, with some basic model configurations. So, does it work for global simulations, regional simulations, variable resolution simulations, simulations with dynamics only, which is important because, we want to use MPAS as a die-core in CAM without using the WRF physics, et cetera, et cetera. So the idea here is that we could probably provide some simple testing harness, or at least some prepared run directories for these different cases, so that you could easily just link in your compile executable and run through these cases and make sure that they all work. So that's the idea. So finally, after we're happy with the pull request, we merge it. And the idea is that all of the commits from your feature branch that weren't already in the main repository get pulled in to the main repository on GitHub, and we get a merge commit that combines the base branch, in this case the develop branch, with our feature branch, in this case the adaptive timestep branch. So there's a couple of things to point out here. We don't copy over the branch pointer into the main repository. The changes have been integrated, so that branch, from our perspective, is no longer needed. But secondly, GitHub doesn't automatically update your fork of the repository. So after your pull request is merged, it's up to you to update your develop branch to match the updated develop branch in the main repository. So as I said earlier, unfortunately, all of the things we've just talked about aren't written down anywhere. Again, we're working on it. So it's worth pointing out that I think we're probably going to ensure that this MPAS contributors guide is itself in a repository. So the idea is that it can evolve as our development process evolves. And also, if anyone in the community finds ways to improve that contributors guide, you could make pull requests to that repository to improve the process by which we handle pull requests. So for now, of course, we're always happy to help. And if you have questions right now, the place to go again is probably, for the time being, to go to the code development section in the MPAS atmosphere support part of the WRF MPAS forum. Okay, so we'll stop and take a sip of tea here, and then we'll talk about model code structure. Okay, so in this section, we're going to get into some of the details of the structure and layout and some of the infrastructure that's available in MPAS. And the idea is that these are things that might be useful to anyone who might want to actually start doing development on the MPAS model itself. So again, we're trying to take a broad view here and say that ultimately you can, and I'm doing air quotes here, contribute or develop anything from post-processing tools to web pages to the user's guide in repositories. But we're focusing now on the model itself. So I'll spend just a couple of minutes to give a quick high-level view of the generic code structure. And then we'll start in and we'll talk about how the physics schemes in MPAS are connected to the rest of the model. And that's obviously going to be of interest for anyone who might want to introduce updated or new physics schemes. And then we'll take a bit of a digression and talk about this thing called the registry and this associated thing or things called pools. And then we'll wrap up by talking about the diagnostics framework that's available in MPAS right now. So at the very highest level, in a generic sense, you can think of MPAS as a driver level that essentially just calls init, run, and finalize methods, and a collection of infrastructure modules that are available for doing parallel I/O, for doing halo communications, interpolation, adding timers in the code, calendar sorts of operations like dates and times, all of that sort of thing. And then there's this idea of a core. So a core is any sort of specific computation that's driven by the driver and that makes use of the infrastructure. So collectively, I guess we could say that the driver plus infrastructure would be something like the MPAS framework. So what is a core? Well, this could be, the atmosphere core, which when compiled in the MPAS framework gives us MPAS atmosphere. It could be the init atmosphere core, which when compiled gives us the init atmosphere model program, which we use, I think most of us know, for creating initial and boundary conditions for MPAS atmosphere. And there's also the ocean and land ice and sea ice cores. And we've even written a testing core, which basically just tries to exercise the infrastructure. So at a very high level, again, speaking generically about MPAS, the first thing that happens in the driver is that a routine called MPAS init makes a call into various parts of the infrastructure to initialize all of the infrastructure. The next thing that happens is that this MPAS init routine then turns to the core and says, all right, core, you can initialize yourself. And that core in turn may then make use of the infrastructure to read initial conditions or read a nameless file or read a streams file or something like that. And then once everything is initialized, the driver tells the core, okay, run, whatever that means to you. So if you're the init atmosphere core, running means creating initial conditions. And if you're the MPAS atmosphere model, running means running a simulation. You get the idea. And then as you expect, after the running is finished, the driver finalizes the core and then gives the infrastructure a chance to finalize itself to close any open files and deallocate memory and that sort of thing. So if we look at the MPAS atmosphere core specifically, inside of the core atmosphere directory, we have a Fortran module called ATM core. And it's this module that implements the init, run, and finalize methods that are called by the driver. So if you ever start exploring the MPAS atmosphere code and want to get to a known starting point, go to the ATM core module and start there. So the init and finalize are in some sense a little bit boring. They do exactly what you'd guess. They read initial files, read lookup tables, and that sort of thing. And it's the run method, the ATM core run routine, where a lot of the interesting work happens in some sense. So it's in this routine where we have the implementation of the main time stepping loop. And it's this loop that is responsible for making all of the calls to the physics, to the dynamics, to the diagnostics. And it's also the routine where we handle periodic input and output. So we write out model history files periodically, and we might periodically read like SST or sea ice updates. So, just based on our experience with WRF and our experience so far with MPAS, we're anticipating that most of the contributions from the community to MPAS atmosphere will probably come in the form of new physics schemes or new diagnostic modules or diagnostic computations, and probably less so in the form of changes to the dynamics. So we'll spend a little bit of time in this section then talking about the physics and the diagnostics, and we'll not really say anything else about the dynamics. So starting right in with the physics, essentially there are 4 points that the physics interact with the rest of the MPAS atmosphere model. And so what we're looking at here on the left is kind of a very high level and pruned calling tree, starting at the ATM core run method. And so it turns out that the physics are connected up through these points that are highlighted with yellow arrows here. So just walking through this call structure, again, at the high level, we've got the ATM core run routine, which is, as we just said, the main run routine that's called from the MPAS driver. And it's responsible for taking time steps one at a time until we get to the stopping point of our simulation. And in the course of doing those time steps, it calls physics, dynamics, diagnostics, and stream I/O. So the first thing that happens in the core run routine is that we basically call ATM do time step. And this is the routine that's responsible for advancing the model state by one time step forward in time, which essentially means, physics and dynamics. So the very first thing that happens in the ATM-do time step routine is that we make a call to a routine in the physics directory called physics time tracker. So this is the routine that's responsible for handling periodic updates to surface, SST, and deep soil fields. But it's also the routine that's responsible for checking alarms that may be ringing that tell us that it's time to call certain physics routines. So you might have set in your name list an option to say, oh, I'd like to call the radiation schemes every 10 minutes, for example. So some alarm gets set, and it's the physics time tracker routine that checks. And when that alarm is ringing, it says, aha, we've done 10 minutes of simulation. Now I'm going to set a flag that tells the physics driver, which we'll talk about next, that yes, this is a time step in which we need to call radiation. Or maybe you've said you want to call the PBL scheme every 5 minutes. Those sort of alarms are handled in this physics time tracker. Immediately after that, the ATM-do time step routine makes a call to the physics driver routine. And we'll get into more details of this in just a couple of slides, but essentially this is the main driver that is responsible for calling all classes of physics schemes except for microphysics. And then after that, we call the ATM time step routine. Probably we should rename this to something like dynamics driver, because ATM time step is eerily similar to ATM-do time step. I think the reason for that is purely historical. So we may rename this at some point in the future. Essentially, this is the main dynamics routine that takes a full integration time step. And right now in MPAS, this is a very thin wrapper around the ATM SRK3 routine, which is the main split RK3 integration routine. So in addition to doing all of the dynamics things that you'd expect, this ATM SRK3 routine calls a routine called physics get-tend. And this is the third point in which the rest of the model interacts with the physics. And it's this physics get-tend routine that's responsible for producing tendencies to the prognosed dynamics variables on the proper staggering from all of the tendencies that were provided by physics schemes in the calls from the physics driver. And then at the very end of the ATM SRK3 routine, we make a call to driver microphysics. And as you can guess, this is where we call the microphysics scheme that does a direct update of the model state. So if we expand the physics driver, this is, as we said, the main routine for handling calls to all classes of physics schemes. So LSM, surface layer, PBL, convection, shortwave and long wave radiation, gravity wave drag, maybe cloud fraction schemes, maybe other things that I've forgotten. So, we'll just talk about the PBL scheme here, but again, the same idea applies to these other classes of schemes. So at any rate, the very first and last things that happen inside the physics driver are calls to allocate and deallocate for all physics. And what happens here is that we allocate arrays that are needed by the physics schemes using the right array dimensions. So all of our physics schemes right now come from WRF. And in WRF, there's more or less an expectation that arrays have this IKJ ordering. And that's different from the array ordering that we use in MPAS. So we need these interstitial or intermediate arrays to hold MPAS fields. So that's what gets allocated and deallocated at the beginning and end of the physics driver. Next, the physics driver calls this MPAS to physics routine, which essentially just copies or transposes all of the MPAS arrays that are needed by multiple classes of physics into these arrays that were just allocated. And then we call allocate something. In this case, again, we're talking about PBL, but the same idea applies to surface layer and convection and radiation and so on. So here we allocate just the transposed arrays that are needed only by PBL schemes and deallocate them. And then if we look a little bit more into the PBL driver or the convection driver or the surface layer driver, we'll see that we do the same sort of thing. It's called PBL from MPAS. So this takes all of the MPAS arrays, transposes them, and puts them into the PBL arrays that we just allocated. And then we've got this generic block that says call specific PBL scheme. So this is the logic inside the code that says, all right, in your name list, you've said that you wanted the Mesoscale reference suite, which implies that we're calling the YSU PBL scheme. Or you've chosen the Mesoscale reference suite, but in your name list, you said, I want to override the surface layer and PBL schemes with the MY and N schemes or something like that. So those specific calls happen down in these class-specific drivers, if we could call them that. So that's the idea. It's a fairly brief tour of the calling structure for physics, but hopefully that gives you enough to go on if you wanted to poke around and start adding a new physics scheme. So just a couple of other notes about contributing physics. And this is not to say that this is the case right now, but moving forward, we would really like for all contributed physics schemes to be model independent or model agnostic. So this means that we don't want, any assumptions about particular grid staggerings or things like that. And maybe without some care, and this is just me guessing here, this probably implies that maybe a lot of these schemes are probably column independent. Otherwise, they would need to know something about the horizontal grid of the parent model, although there are probably ways around that. But in general, and try to keep these model independent, don't make calls to, WRF message or things like that, if we're going to be using the scheme in CM1 or in MPAS. Secondly, we'd really like for you to document the scheme's input and outputs according to the CCPP standards. So there's more details on that that we'll make available in the near future. And then lastly, and this isn't the case right now, but we'd ultimately like for all of these new physics schemes to go into a shared repository that the WRF model, the CM1 model, and MPAS can all pull from. So on that last point, if you're interested, sorry, could someone mute their microphone there? Great. There's a talk tomorrow by Laura Fowler called Shared Physics Repository for WRF, MPAS, and CM1. So you may want to check that out if you're interested in hearing more about the efforts to get a unified physics repository. Okay, so now we're going to digress a little bit and talk about some infrastructure. And so we'll talk about this thing called a registry and these associated things called pools. So if you're familiar with WRF development, you are probably already familiar with the idea of a registry, but as we'll see, the registry in MPAS, although similar in concept, is different in its implementation. So it's syntactically different, and even some of its functions are a little bit different from the WRF registry. But in any case, whether you know about WRF or not, basic idea is that the registry in MPAS is an XML file, and it's also a program that goes along with that, that we build at compile time and which operates on this XML file. And the basic idea is that in this XML file, we can very concisely define things that would otherwise require us to write really boring copy and paste code. So not only is this sort of code tedious, but it's also error prone. So you copy and paste in a couple of different locations and you forget to consistently change things across all of those locations. So that's something that's not really great to do as a human, but it turns out that computers love doing this sort of thing. So that's the idea behind the registry. So a couple of things that we can define in these registry XML files would be things like name list options, new packages. I won't say more about packages, but if you've worked with WRF, you probably know what packages are. New model variables. So anytime you're doing development, if you're adding, for example, a new diagnostic, certainly you want new variables to hold the diagnostic that you're computing. So you do that in the registry. And you can also define or modify the default IO streams for any MPAS core, whether it's the init atmosphere core or the atmosphere core. So that implies this idea that every core has its own registry file, which makes sense because MPAS Ocean probably wants a completely different set of name list options and variables from MPAS Atmosphere. And then pools are something that are very closely related to the registry. And essentially, they're these derived types that are dynamically instantiated when any MPAS core starts up. And essentially, they contain all of the things that you've defined in the registry. But at the end of the day, you probably don't care about these data structures. You just say, I want to get things from them. I defined a whole bunch of variables in the registry, and I want to get those variables or get references to those variables. So along with pools, we provide a set of routines that allow you to pull things or get access to the things that are stored in these pools, i.e. the things that you defined in the registry file. So there's probably actually 6 or 7, but we'll just say that there are really about 5 primary things that you can define in a registry file. And the first of these, and the most easy one to talk about, is a name list option. So when you compile MPAS Atmosphere, if you've looked inside the MPAS Atmosphere name list, you'll see that you've got, for example, a nameless record or nameless group called damping. And inside of that, we have an option called config ZD, whose default value is 22,000. And so you could say, where does this come from? When I get a fresh clone of the MPAS repository, if I grep around, I don't see config ZD defined anywhere as a nameless option. So it turns out, of course, because we're talking about the registry, that this is something you define in an XML file. So the corresponding definition of this damping nameless record and this config ZD nameless option looks like the following. So we've got an XML tag called NML, or nameless record. Its name, of course, is damping. This in defaults option basically allows you to hide options. So you can say, I'd like to be able to control things at runtime through the name list, but these are tuning knobs that I think a general user probably shouldn't see. And so I'm going to say it's not in the default streams file that's generated at build time. So you could say in defaults is false. And then, of course, we've got nameless option. Its name is config ZD. It's real instead of integer or logical or a character string. And here we see that its default value is 22,000. Also, we see that we've added a couple of extra attributes. So we've got units and description and possible values added to this nameless option. And these are things that don't show up in the registry file. But if you look inside of the MPAS users guide, you'll notice that these exactly correspond to things that appear in appendices. So it turns out that we use the registry file not only for generating parts of the MPAS code, but we also use it for generating documentation as well. So also in the registry file, we can define dimensions. I think this is pretty self-explanatory. We're defining two dimensions here called end cells and invert levels. It is also possible to define dimensions that have a specific size. So for example, we could say that there is a dimension called n months. And by definition, that is 12 because we always assume that there are 12 months in a year. So anytime you define a dimension without a specific size for that dimension, it's assumed that this dimension will be found in the initial conditions file for MPAS in this case. So we can also define groupings of variables, which we call variable structures, and which we probably should call pools, because it turns out that every one of these structures or groups of variables gets translated into a pool of things that you can access inside of the code. So here we're defining a grouping of variables that we're going to call mesh. And we're saying that all of the variables in this mesh structure or group have just a single time level. But the more important thing is that we can define variables inside of these groups. So here we're defining, again, this is probably self-explanatory when you look at it, but we're defining a new variable called lat cell. It's real, it's dimensioned by n cells. And of course, n cells is a dimension that we have already defined in the registry. And we're defining another variable here called lon cell. And again, these have a units and description, which you can access in the code, but are really not used except when we generate documentation, appendices in the user's guide. And then lastly, you can set up new default IO streams, or you can make changes to the default IO streams. So after you compile MPAS, you might say, where was it decided that the diagnostic stream contained the following set of variables? I'd like to propose that we change that. You could change that in the registry. And if you thought everyone else might be interested in that change, that's when you could make a pull request, for example. So just a couple of quick words about where the registry has an impact on the model. Essentially, this is a compile time thing. So during the compilation process, there's a dependency in one of our make files that says we need to run this little program that I talked about earlier to parse the registry XML file for a core and to automatically generate a lot of Fortran code. So if we take the atmosphere core as an example, we're looking at a directory tree here down in the lower left, we'll see that we have a registry file for the atmosphere core. And after you compile the model, you'll see that you've got this inc or include directory. And it's inside of this directory that all of the automatically generated code gets placed. So just for fun, if you're bored, you can go ahead and look in this directory and see what some of the auto-generated code looks like. And for MPAS Atmosphere right now, it's something just a little bit short of about 19,000 lines. It sounds like a lot, but I think it's just guessing it's probably maybe a couple 100,000 lines for WRF or something like that. So we're trying to get away from the idea of generating a lot of code and instead just writing more generic and more dynamic code in the first place. But there are still some things that are much easier to do by actually just writing code. But that's the idea, is that this is a compile time thing. So as a consequence, if you make any sort of changes to the registry file, you'll have to recompile the model. So these pools, I said, were dynamic data structures, but more importantly, there's a set of routines that go along with them that allow you to access all of the things that you defined in the registry from these pools. And so these routines generally have names like MPAS pool get something. And so using these routines, there's a few different things that we can query in your Fortran code. And these all happen at runtime. So if you want to get a reference or a pointer to one of these groupings of variables that we defined, in the example that we saw earlier, we were defining a structure or group called mesh. But let's say that we also defined a grouping of variables that represented the dynamical state as a model. So we could get a reference to that grouping of variables with a call to MPAS pool get subpool. So that's my comment earlier. I said we really should have just renamed structures as pools because you access them as subpools. So it turns out that a pool can contain another pool. You can also get references to nameless options. So here we're saying that from a pool called configs, I want to get something which is, this is a string literal here called config DT. So this is exactly the name of the nameless option. I want to get a reference to that with this variable that in my Fortran code is called DT. You can get dimensions. You can get fields as derived data types. So this is a derived type that describes, in this case, the theta m field, which allows you to access things like the names of the dimensions, the missing value for theta m, its units, its description, and so on. But more often than not, what we really want is just a pointer or a reference to the actual array storage for a field. And we can do that with this routine called MPAS pool get array. So the idea is that if you look around in the MPAS code, you'll see all of these calls to MPAS pool get, MPAS pool get, MPAS pool get. The idea is that we're just trying to get references or pointers to all of the things that we set up in the registry file so that we can actually do computation. And what we'll do after this workshop is we'll make available a full set of slides that has some nice example of how you can use these pools to do some useful computation, to apply some number of smoothing passes to the terrain field by defining variables in the registry and making these MPAS pool get calls. So in the interest of time, we'll not go through those now, but those will be included in a full slide deck. So that brings us then to the MPAS Diagnostics framework. So the basic idea here is that some years ago, we didn't have any sort of structured way of adding new diagnostics in MPAS. And we realized very quickly, even just among contributions from people in our small group, that without a structured way of doing this, things became pretty chaotic. Not really in the Lorentz sense, but in the disorganized sense of the word, I guess. So we ended up developing this MPAS framework that supported the implementation of various sorts of diagnostics. So this framework allows you to write instantaneous diagnostics, so things that are computed at an instant in time based on the current model state, but also diagnostics that need to compute values that are, for example, accumulated over any arbitrary period of time. Also extreme value diagnostics, which I guess you could argue are basically the accumulation of extreme values or pointwise minima and maxima over periods of time, or generally anything that looks like these things. So anything that's computed at a point in time or over a period of time, we can support with this diagnostics framework. But as we'll see, it's also helpful if your diagnostic can respond to changes to streams that might write out your diagnostic. So you might want to know in your diagnostic, how often am I being written to an output file? And maybe I want to do something different based on that. So we'll look at a really quick example to wrap up this diagnostic session where we do just that. So essentially, when you write a new diagnostic for MPAS, you need to think about how to break up your computation into 5 stages. So the first of these stages is what we refer to as the setup stage or setup phase of a diagnostic. As you can guess, this is something that happens once when the model starts up before we ever take the first model time step. So the idea here is that, maybe you want to pre-allocate arrays that are going to be used by your diagnostic. Maybe you want to initialize some variables. Maybe you want to read in some input files, anything like that. The second stage is the update stage or update phase of the diagnostic computation. And this is called every time step that the model takes. So this is your chance generally to accumulate values update extreme values, something like that. And then immediately following the update phase is what we call the compute phase. And I would say the distinction here is that compute is generally where we tend to finalize computation. So if it's an instantaneous diagnostic, this is where we finalize that computation. And if it's a cumulative diagnostic, maybe this is where we divide by delta t to get a mean value over that time period or something like that. And then lastly, at the end of a time step, we call the reset phase for every diagnostic, that it gives your computation a chance to reset itself if it so chooses. And then finally, probably self-explanatory, is the cleanup phase. This happens at the very end of a model simulation, and it allows you to close files, deallocate memory, whatever you want. So I think the setup and cleanup phases, again, are pretty obvious what those do and where those sit. But what about these other phases? So where do they fit into a time step? Essentially, we've got our time step loop here that, as we said earlier, in the ATM core run routine, just gets called over and over again until we reach the end of a simulation. So the very first thing that happens in a time step is that we advance the model state by calling physics and dynamics and microphysics. Immediately after that, we call the update phase for all diagnostics. Then we call the compute phase. And critically, this happens right before we write any sort of output streams. So again, the compute phase is your chance to compute whatever you need right before we potentially output your diagnostic. And then after all the stream output happens at the very end of the time step, we call the reset phase for all of these diagnostics. So the key idea here is that you probably need to know whether your diagnostic is going to be written in the time step or not. So in the compute phase, the question is, do I need to compute myself or not? If I'm going to be output, in the very next call to stream output, then I'm going to compute myself. Otherwise, I'm not going to do anything. So in addition to this diagnostics framework, we do provide a utility module that allows any sort of diagnostics that you write to determine two things. So firstly, whether your diagnostic in any given time step is going to be output or not. But secondly, how many output streams include your diagnostic. So you can imagine why this might be useful. If you query the number of output streams that contain your diagnostic in the setup phase, and that number happens to be 0, that tells you that there's no output stream that the user has set up that's going to be writing your diagnostic. So maybe you just set a flag that says, don't even bother computing this diagnostic. No one's ever going to see it because it's never written out, for example. So in terms of code organization, the idea is that we wanted these diagnostics to be essentially self-contained and not scattered all throughout the code. So just very briefly, if you look inside the core atmosphere directory, you'll see that there is a directory called diagnostics. So that's ultimately where you need to implement your diagnostic code. And we said, just earlier that we want the definitions of all variables to live in this registry XML file. So it turns out that what we have inside the diagnostics directory is a registry diagnostics.xml, where you can define your new variables for your diagnostic. And this registry diagnostics file, in turn, is included through pre-processing directives in the main registry. And then inside this diagnostics directory, there's also the MPAS ATM Diagnostics Manager, which basically allows you to hook in your setup and update and compute and reset and cleanup phases for your diagnostic. So in that way, it serves as the connection point between your interface and the rest of the model. So if you want to add a new diagnostic, there are really just 4 easy steps to doing this. So the first thing is that you'll probably want to define all of the new variables for your diagnostic in its own XML file. So let's say that we're making a foobar diagnostic. The idea is that we'll probably make a file called registry foobar.xml, and we'll include that in the main registry diagnostics. Then we'll actually write the code that implements all of the phases of computation for our diagnostic. Then we'll hook in those calls into the main diagnostics manager. And then the thing to not forget is to actually edit the make file so that we actually compile your new code and link it in with the rest of the model. So there is a README in the diagnostic subdirectory that talks about these things in, I think, maybe only slightly more detail. But that's the basic idea. It turns out to be quite simple. So to convince you of that, we'll just look at a very simple diagnostic. So the idea is that maybe for whatever reason, we wanted to look at the maximum shortwave downward flux over an output interval. So we're going to call our new diagnostic fields GSW max. And what we want this to represent is the maximum pointwise. So for every grid cell, the maximum shortwave flux over whatever interval this field is written to an output stream. So if we're writing this field to an output stream every hour, we want that to be the 1 hour maximum. If we're writing this field to an output stream every 6 hours, we want it to be the 6 hour maximum. Hopefully that makes sense. So after we've essentially added like 6 lines of XML to a new file, as we said, we connect that to the main registry diagnostics with just a simple pound include line. And then we implement the setup and update and reset phases. So the setup phase makes probably a lot of these MPAS pool get routines. And while we're at it, maybe we'll just initialize GSW max to 0. The update phase is probably the shortest function you will ever write. It's literally a 1-line function that says GSW max is the max of GSW max and the current time step downward shortwave flux at the surface. And then the reset phase says if the field GSW max will be written, in this case, the verb tense is not quite right. This was just written because we're at the reset phase, then 0 out this maximum field because we're going to start accumulating maxima over the next output interval. And that's essentially it. So in the interest of time, I'm just going to say very quickly that if we then, so again, to point out, we've written like 8 lines of code in XML files and maybe a couple of dozen lines of Fortran. And that's really it. So by doing just those things and adding GSW max to an output stream, if we output that field every 60 minutes at 0 UTC, maybe the field looks like this, and we can convince ourselves that, yeah, this is probably where the sun should be at about 0 UTC or the hour leading up to 0 UTC when we output this field. And if we output this field every 24 hours, that gives the Earth a chance to rotate through 360 degrees. So we get some shortwave flux just about everywhere on Earth, and you can pick out clouds and other interesting things there. So that's the idea. So I think we had a 5-minute break scheduled now. I don't know whether we want to do that or not.
We only have 10 minutes left, so I suggest you continue moving along, Michael.
Okay. Sorry, everyone who was anticipating a break. We'll go through this last part pretty quickly because it's a fairly high-level overview of some of the areas where you might want to contribute. So essentially, if you want to get involved, whether it's writing Fortran code or anything else, there are plenty of opportunities. So, traditionally, we say get involved in model development, and you think, all right, that's got to be physics or dynamics. But we just finished talking about this diagnostics framework, and it turns out, hopefully, as I convinced you, that writing diagnostics, can be a very simple process, and yet diagnostics can be really useful. So contributing new diagnostics to the model is certainly an easy and very helpful way to get involved in development of MPAS atmosphere itself. But broadening our view a little bit further, besides the atmosphere core, we also have the init atmosphere core where we create initial and boundary conditions. So here there are plenty of opportunities. For example, if you wanted to add new idealized test cases, or maybe you wanted to improve something about how we produce real data initial and boundary conditions. So maybe you say, it seems that it's not currently possible to initialize regional real data simulations with her output. That would be really great. Maybe that's an area where I could contribute to the init atmosphere core. Stepping even further back, but still looking inside of the MPAS model repository. If you happen to be like me and your background is in computer science, you say, well, maybe I don't do model development, but maybe I'm interested in parallel computing or algorithms or generally computational infrastructure. So maybe, there are opportunities to contribute to the shared computational infrastructure. And if you get in contact with us, I'd be happy to throw out half a dozen great ideas where we can optimize, clean up, and generally improve the infrastructure. Of course, after we run the model, presumably most of us are running the model because we actually want to do something with the output. And so as you can guess, there are many, many opportunities to contribute different tools for doing visualization and post-processing, especially if these are Python-based, since it seems that there are many communities that seem to be converging on Python as a common language for doing a lot of things, from machine learning to graphics to data analysis. And particularly if these tools work directly on the MPAS unstructured mesh, that would be great. But even further, if you happen to have a talent for communication and writing, we want to get the MPAS Atmosphere Users Guide into its own repository. And so there are plenty of opportunities to help us improve that. or even improving things like the online tutorial. If maybe you want to help us out and contribute new tutorial exercises, we'll be happy to include those in future tutorials and to make sure that you get credit. And you can also make changes even to the MPAS webpage. And here I'll simply say that, even if you don't want to write code of any sort, if you happen to have a publication that uses MPAS, you can make a pull request to the repository that houses the webpage to get your publication included on the publications page. And again, you do that through a pull request. So there's one way that you can start using GitHub just to let other people know about your paper. And, essentially, in my opinion, this is almost as important, or probably more important, than making code contributions. It's just being an active member of the community by participating in the forum. And if you have experiences with any part of the MPAS modeling system and want to help out other people who might have questions, participation on the forum is always really greatly appreciated and very much valued. So if this sounds exciting, where do you get started? As we said earlier, maybe just start talking to us, maybe on the forum. But if it's discussing a particular development in a repository, once we probably enable GitHub discussions, maybe doing a discussion on the particular repository is the way to go. So I won't say anything about the repositories that we have or that we plan to make. Those are pretty self-explanatory. The last thing I'll point out is that you may want to contribute to the MPAS ecosystem by developing your own package, but you want to be the maintainer for that package. And so you're developing it in your own repository. So how do we bring all of these things together? Essentially, again, let us know that you're working on, for example, some analysis package, and we'll be happy to do some significant modernization and revamping of our visualization page, maybe to have a nice graphic and short summary of these different community contributed tools. And then we'll link to whatever it is you're developing. So essentially, we'll be happy to try to provide advertising for whatever it is you're working on. So hopefully we'll still have some time for questions. For me, it's lunch and I'm happy to stick around and talk. But I know that it could be dinner time or something else, or maybe it's like 3 a.m. for other people. So I'll just leave up this summary slides and maybe we can take questions. So I don't know if you want to place a question in the chat or raise your hand and we could just call on you to say your question.
So Michael, are you seeing the chat?
No, so I'm trying to exit presentation mode so that I can see the chat.
Okay. Yeah, so the first question is, will documentation for MPAS be transferred to a repository on GitHub? And the answer to that is yes, it's our intent to do that. You want to say anything more about that, Michael? That's more your area.
Yeah, so sorry, I was just looking, I guess I just opened the chat now, and it's a wonderful feature of Zoom that it doesn't show me the past history of the chat, apparently. So the question was about whether we're going to be transferring the user's guide to a repository, right? And the answer is yes. So right now, it turns out that we do have an MPAS documents repository, and we have the LaTeX source for our user's guide there. But I think we'd like to move that into its own repository, firstly. And secondly, I mentioned in a bullet that we'd like to maybe convert that to restructured text. And then that allows us to use Sphinx to either turn that into nice web pages or to create PDF versions of the user's guide. So I think there's going to be some significant refactoring of our user's guide in the future. Sorry, I can't see if anyone has their hands raised or anything.
So the next question that's come into the chat is, what's the planned timeline to start opening these repositories? A few months? And I would say yes, at least for some of them.
Yeah, I would agree. And, the other thing too is if we start getting nudges, hints from the community, like, hey, it would be really great to have this particular repository, we can prioritize these, essentially however we want. So, maybe just dropping us a line and saying, hey, I'm really interested in the online tutorial. I'd like to adapt that so that I can use it in, my research group at my university. I want to adapt it for our university's computing cluster. So if we could get that in a repository, I could make a fork of that and change all of the directory names and that sort of thing. So, letting us know what you'd like us to prioritize is certainly a possibility.
One of the things we're moving on with hopefully in the very near future is the shared physics repository between WRF and MPAS. And of course, so many things come in for shared physics that we're really putting a prioritization of that to move it quickly. So.
Yeah, see, there's a question in the chat that says, is there any alternate way to use direct input data for MPAS apart from using the WPS to pre-process the data? And that's a really good question. So we essentially inherited this intermediate file format from the WPS, and we said, well, it's a format that we're already working with and it's easy to read. But that would be an interesting thing that we could discuss. So you could imagine that we could use, NetCDF files directly in the init atmosphere core. The difficulty there is that NetCDF enables a lot of flexibility. So we don't know anything about the names of dimensions, the orders of dimensions, whether 3D fields are split into separate layers for every, or separate 2D arrays for every layer, or stored as 3D, is it, bottom top or top bottom. So the downside to other file formats is that there's a huge amount of flexibility, and there's no, real standards to say, this NetCDF file contains data on a Lambert conformal projection and has this grid spacing and so on. So I think that might be the real difficulty there, is that other file formats provide almost too much flexibility. But that being said, maybe we could define a standard for a constrained NetCDF file format that says you must have the following global attributes and variable attributes and so on. So that's something that we could definitely work on.
Michael, perhaps, I don't know if everyone is aware, but I think we recently added a compilation option to compile ungroup only without you, because to compile WPS, you need to compile WRF and so on and so on. But the ungroup compile only option may help in that regard, right? You only compile that single program to create intermediate file.
Yes, so this is good, and I'll put this in the chat. I think this is just from memory, so you might try these and they're wrong, but we added 2 new options. Well, one of them was already there, but we added a new option in the latest release of the WPS so that you don't have to compile the GRIB2 libraries yourself, and you don't have to compile WRF. So if you get the 4.4 release of the WPS and you configure with --no WRF --build -grib2 -libs, there are no dependencies. We have built-in copies of all of the GRIB2 libraries, and you don't need a compiled WRF code at all. And you get an ungrib executable that can then run by itself. So we've tried to make the ungrib functionality as standalone as possible in the latest release. So at least that's a step in the right direction.
So Koichi has another comment here about contributions, for example, make files or the user guide section, et cetera, that those should be communicated through the support forum ? And I would say that's certainly one way to communicate that, for sure.
Right. And so, yeah, this again is the idea that we could enable GitHub discussions on all our repositories, and we've just never used them before, so we don't know whether they have any major drawbacks. I was playing around. It turns out that you can enable them and then later disable them. So if we could just go through and enable these on all of our repositories, this week, and see how it goes. So maybe that's a possibility, is to target the discussion to a particular repository. Maybe we could use GitHub discussions.
Mm-hmm. And almost asking, are chemistry aerosols going to be available in MPAS-A, or is that coming only with CIMA? At this point, what I can say is it's certainly coming with CIMA, and it's still an open question whether we're going to try to bring significant capabilities of chemistry and aerosols into the standalone MPAS. Some of this is resource issues, and also, yeah, I'd say most of it's resource issues. But CIMA definitely will be there, and everything that's available within CESM in that regard will be available to MPAS-A, and in some sense already is, although we haven't officially released it to the community yet. Yes.
Oh, wow, we're getting questions from YouTube. So there's a question here. How is the data assimilation module planned in this version of MPAS Atmosphere?
So you have access already within the standalone MPAS Atmosphere to both Dart which is a data assimilation research testbed, which is an ensemble common filter. And also the JEDI, which is a joint development with NOAA and a whole bunch of other folks, including folks at NCAR. So you have access to both of those already in releases that are already out there. So if you go to the DART and JEDI pages, web pages, you can find information for how to access those, or you can ask appropriate questions on the forum or to us directly. If I'm not quite sure what our data assimilation section in the forum looks like and who monitors it.
Yeah, I don't know that we really, so the data assimilation section on the forum seems to be really tailored to like WRF DA.
WRF DA, yeah.
So maybe this is a thing that we need to do, is to think about and probably talk to the JEDI group to see, you know, how can we start to provide MPAS specific support for JEDI?
Yes, so, and who to direct them to. If you go to the JEDI web pages, I'm sure you'll find information, and if you can't, ask us and we'll direct you appropriately.
I believe Jake Liu will have an update on MPAS JEDI tomorrow in the updates, development update section of the workshop.
Yes. Okay, we're at noon, 3 minutes after. If
Perfect.
there are no more questions, shall we close the session, Wei?
Yes, yes. And we'll see you tomorrow morning at the same time, 9 o'clock, when we start the meeting. Thank you for participating in today's meeting, and thank you for asking questions and participating in the discussion. We'll see you tomorrow then.
Yeah, and I see there, I'll hang around. I see a few other things popped up in the chat here, so I'll hang around and try to answer those.
Oh, okay. Yeah, let's not leave close the meeting yet. Okay.
Yeah, so thanks everyone. Hope this was interesting or helpful, or both.
So Michael, oh, sorry. So Michael, you want to, yeah, just go.
Yes, I guess we can, yeah, say these out loud. So someone is asking, if someone wants to do work on WRF ARW, is there another way to do it through this? And I would say the WRF model probably has its own development process that's pretty firmly in place. And that's not to say that over the next several years, we might try to unify the development process, you know, or to have more parallels between the process that's used for WRF development and MPAS development. But maybe Wei or Kelly wants to say something about that, if Kelly's here, that the WRF model kind of has its own process and it's not always exactly like what we've talked about here.
I would say really it's very much like you have described. We probably, yeah, using GitHub branches, GitHub, the WRF model is in the GitHub repository, and we have a host of documentations on GitHub you can read and yeah, start your contributing, if that's what you're thinking of, contributing. Very similar. There may be a detail too that's a little bit different, but it is very similar. We have a support page that outlines the requirement for contributing to the model code, and yeah, I think in general they have a lot of similarities. Yeah.
So there is one more question from Koichi. Any standards for commenting in a source code will be included in the developer's documentation? Like standards require, like for Git commit descriptions? And the answer is yes, although we'll try to enforce these gently. So we'll provide them as like strong recommendations. And I was thinking about this over the past couple of weeks, that at least I like to see examples, right? So you can tell me, you know, this is what I want a code comment to look like. But what's sometimes helpful is just having a catalog of examples to say, here's what we think is, you know, a good example, and here's why. Here's what we think is not a good example. And these will be made up examples. We're not going to actually point to anyone's code. So the answer is yes. We'll try to provide as much guidance as possible as to, what, and recognizing that this is our opinion, what represents good code comments. And again, providing plenty of examples so that you can look through and say, all right, I get the idea here. So the short answer is yes, that is something that we definitely plan for the contributors guide. Sounds good. I see a comment that we'll bring some of these up in the discussion forum. So we look forward to that.
Do you see more questions? Looks like.
No, I think maybe that does it.
Yeah. Well. That should do then.
Yeah, I guess if there are no questions, Ryan, from YouTube, then I guess that wraps it up. And thanks again, everyone.
Thank you, Michael. Thank you, Wei.
One last question. Sorry, you always say, is there any last questions? So a question about will new meshes be available? The answer is yes. So go ahead and just ask us in maybe the running or science, probably the science section of the forum. And we'll be happy to generate those if we can see that they would be of general community interest. And I didn't say anything about this, in the longer term, we do recognize that we need to make more mesh generation capabilities available to the community. And the first idea that we had, so we're revealing some really cool ideas, that if we could provide a capability even to make perfect hexagonal meshes at arbitrary resolution on a projection plane, that would allow people who wanted to do high resolution regional simulations a way of generating, a 300-meter, real data mesh over Colorado or something like that. Variable resolution meshes are a little bit trickier, but we can start simple and start with uniform resolution meshes. So we recognize that that is a limitation for sure. A question from Alan, and the name sounds familiar. I don't know if Alan, you might have participated in one of our tutorials, but if you're doing something with MPAS for your PhD work, feel free to, if I could volunteer Bill also, but feel free to email me or Bill or anyone else, and we'll be happy to talk with you about that. All right, and if there are any further questions, feel free to reach out to us either through email or through the forum, and we look forward to hearing from you all. So thanks again.